Hey guys, welcome back to Trick Code. Today we're doing another Brainstellar Quant puzzle. This one is called the Monty Horror Problem. This is a pretty famous probability puzzle. I'll let you guys go over it. So just to explain the problem real quick, we're on a game show and we've been given three choices in front of us. And basically behind one of these doors is the prize, or you could say success, and the other two have failure behind them. Or, well, in this case, it's a car and goats, right? Now, what happens during the game is once you pick one of the three doors as your guess, what the host does is among the remaining two doors, it opens up one of them. And it's guaranteed that behind that door is going to be a goat. So basically, the host knows which ones have goats and which ones have the car behind them. So the host always opens up one of the doors that does not have the car. And he or she gives you an offer if you want to switch your initial guess to the one remaining door, that the one remaining alternate door, do you want to stick with your initial guess, right? That's the problem. So coming to a few hints I'd like to give you guys. Well, first one is pretty obvious, that initially while you're picking any one of the three doors, each door, so this could be probability one is same as probability the car is behind two, or the same probability that the car is behind door three. All of these are equal to 1/3, right? Because there's three cases and each of them are equally likely at the beginning. Now, usually the incorrect solution to this is that people say that it doesn't really matter if you switch or not, since each door has the exact same probability at the beginning. So that should be the same case at the end. And so let's say, well, in the example given to us, the host eliminates door number three, right? And we have picked door number one. So basically, it's asking, do you want to switch between one and two? And now, what usually people think is that, well, door number one, door number two, there's no difference. I don't think there's any difference in switching. So I guess I won't switch. Well, there's a pretty small flaw in this type of logic, and I'll explain why. So in the end, the car has to be either behind door number one or door number two, right? And since these two are the only two cases, and we're arguing that both of these doors have to have the same probability, well, that would mean that both of them have a probability of equal to 1/2, because that's the only way they can add up to one, right? Because the total probability theorem says that all the particular options must add up to one. So, well, how come the probability of door one, which we initially picked, has increased? Well, that can't be possible. Well, if we keep it as 1/3, then we're saying that probability of 2/3 is also 1/3. So those two don't add up to one. So there's also a problem over there. So what's actually going on? Well, the thing is, the probability that the car is behind door number one is indeed 1/3. Well, it was definitely 1/3 initially when we had our first pick, right? There's no doubting that. But this isn't the same case for the door two. So the trick is to realize that the host always picks a door that hasn't been picked by us previously, and it doesn't have the car behind it. The host will always pick a particular door which has a goat behind it, and this is really important. And I'll try to explain this. So say that the probability that we win, given we stick to door number one, is 1/3, right? Now, if I were to ask you guys, what's the probability that we lose, given we pick number one? Well, that's going to be 2/3, right? So what we're saying is probability that the car is behind door number one is 1/3. The probability that the car is behind either two or three is 2/3. Makes sense? Now, what the host ends up doing essentially is since the car can only be behind one of these two cars, if it is behind any of them, it could also be over here. but there's always going to be at least one door among 2 and 3 which doesn't have the car behind it, and it's going to eliminate one of those doors. So all this 2 by 3 probability basically concentrates into the one choice that is left, and this is done by the host, right? The host helps us by basically concentrating all the probability that the car isn't in our initial guess down to one other door, one alternate door. So basically, you have to try to think of it in this way, that the probability of winning, given we pick one, always remains the same. It's 1 by 3, because initially we had 3 options and we're trying to pick any one of them. But the probability that we lose, given we pick one, is concentrated into the only alternate door left, and that is done by the host, and that is going to be, well, probability of winning given one complement, which is going to be 2 by 3. This might not be super clear right now, so I'll try to exaggerate this point a bit. So imagine there were like 100 doors, right? And you pick door number 1. Now the probability that you are going to win is the probability that the car is behind door number 1. Well, that is going to be 1 over 100. And what's the probability that you lose, given you pick number 1? That's going to be 99 over 100. Now what the host is going to do is, among those 99 other doors from 2 all the way up to 100, it's going to select 98 doors that the host knows doesn't have the car behind it, and he's going to eliminate all those cases, and he's just going to give you one alternate door. I'll just call, so imagine that's door number 66 or something, right? I'll just call it the alternate door. So, and now what it's asking you is, do you want to stick with door number 1, or do you want to switch with the alternate door? Now, it's really critical to realize over here that the probability that the car is behind door number 1 is always the same as was initially. It was 1 over 100 because you chose that door randomly. But the probability of the alternate door having a car is the probability of you being wrong initially, right? That's all that the host is doing. So that's going to be 99 over 100. And so it's obviously beneficial, but it's pretty obvious in this case that you should switch, right? Thank you.